Welcome back to the workshop. We have covered modules 1 through 4 and will now review the new pavement design strategies using the Mechanistic Empirical Pavement Design Guide. Module 5 is an overview and discussion of the rigid pavement design strategies themselves. Module 5 will overview and discuss the rigid pavement transfer functions and how they are used to design rigid pavements using the Pavement ME design software. There are two types of rigid pavements, which include jointed plane concrete pavements and continuously reinforced concrete pavements. We will start with the Jpcp rigid pavement design strategy and will overview the three distresses or performance measures used for designing Jpcp. The three distresses or performance measurements include mid-slab fatigue cracking, faulting, and smoothness degradation or IRI. Continuously reinforced concrete pavements will be covered or is covered under Module 5.2. There are 6 learning outcomes for Module 5.1 on jointed plane concrete pavements. The first is to describe the Jpcp transfer functions for mid-slab fatigue cracking. The second is to describe the transfer function for transverse joint faulting. The third is to describe the regression equation for smoothness degradation or IRI degradation. The fourth is to list the assumptions used in the Jpcp design strategy. The fifth is to demonstrate the impact of selected input variables on the predicted distresses. And the sixth is to identify the input variables or design features to be changed to achieve an acceptable Jpcp design. We will also have learning outcomes for each individual jointed plane concrete pavement distress for the individual sections of Module 5.1 on Jpcp, which include the learning outcomes also displayed on this slide. Before getting into the details of the rigid pavement design strategy and discussing the transfer functions that are used in design, there are 3 chapters, 2 to 3 chapters that include information or suggestions for rigid pavement design. The 2 chapters include Chapter 3, specifically Section 3.4, on new rigid pavements, PCC overlays, and restoration of rigid pavement design strategies applicable for use in the MEPDG, and Section 3.5 on design features and factors not included in the MEPDG process. Chapter 5, specifically Section 5.4, on the distress prediction equations and transfer functions for rigid pavements. There is also a Chapter 11, specifically Section 11.2.2, that briefly overviews the Jpcp design strategies themselves. This Chapter 11, or information in Chapter 11, will be discussed very briefly under Section 5.1.4 on interpreting and or adjusting Jpcp's designs for achieving an acceptable design strategy itself. Now let's open the MEPDG Manual of Practice and briefly go through these different sections in terms of what will be covered within this module on rigid pavement design. So this is the MEPDG Manual of Practice, basically the 3rd edition. And we're going to scroll down to Section 3, specifically on Section 3.4. Section 3 is the significance and use of the MEPDG. We're first of all going to very briefly review or note Section 3.4 on new rigid pavement, PCC overlays and restoration of rigid pavement design strategies applicable to the MEPDG, and then Section 3.5, design features and factors that are not included within the MEPDG process itself. We'll then go to Chapter 5 on performance indicator prediction methodologies. This specific module we're under now will go over the distress prediction equation for rigid pavements as well as for the PCC overlays. And we're going to focus on the jointed plane concrete pavements. In other words, transverse cracking, mean transverse joint faulting, and then also smoothness of jointed plane concrete pavements. So going back to 3.4, this is the new pavement design, the different strategies. We're going to go down to specifically the section on rigid pavements. This is Section 3.4. And on Jpcp, and as I mentioned previously, CRCP will be covered under Module 5.2 itself. But this simply gives a brief description of the different types of design strategies, rigid pavement designs applicable to the Pavement ME software. Specifically, Figure 3.3 includes a schematic illustrating the new rigid pavement design strategies that can be simulated with the Pavement MEPDG software or PMID software. This just shows the general layers, the different types of structures that can be considered in designing new jointed plane concrete pavements. Figure 3.4 is for PCC overlay design strategies, which we will get to in modules 7 and 8. Section 3.5 is on the design features and factors not included in the MEPDG process for the different types of pavements. And this is just a discussion of what is not directly considered in the Pavement ME design procedure. Some of these are like geogrids. We do semi-rigid pavements is considered in Pavement ME. And we do have pavement preservation programs that can now be considered. But stage construction, the ultra-thin PCC overlays, jointed reinforced concrete pavements are not applicable to the PMID software for rigid pavement. So now let's go to the Chapter 5. We want to touch on Chapter 5 to go through the different prediction methodologies for the different distresses of rigid pavement. So we're going to start with transverse cracks or transverse slab cracking, both bottom up and top down cracking in jointed plane concrete pavements. This shows the equations that are included in this section to come, or that we're in right now, on a brief description and overview of the variables and other factors considered in predicting mid-slab fatigue cracking. Section 542 provides an overview of mean transverse joint faulting. This will be covered under the module 5.1.2 that shows the approach for using for predicting faults of transverse joints, which we will cover in the module. And then the final on smoothness will be covered at the end of this module on 5.1 for jointed plane concrete pavements themselves. So, and that's going to be under section 5.4.5 of the Manual of Practice, smoothness of jointed plane concrete pavements. Notes the regression equations that's used specifically in the software for predicting how IRI is going to increase over time. So with that, we will divert back to the presentation and then continue. So Module 5.1 includes 3 topics for each individual distress. We will first do a Jpcp distress definition and measurement, a Jpcp distress mechanism, and then the Jpcp transfer functions. These 3 different topics are covered by each individual distress type for the rigid pavement distress model. And this will be the similar approach in this module, but it'll also be used for the CRCP and the flexible pavement design strategies. First defining the distress, then discussing the distress mechanisms, and then explaining the transfer functions. We'll start with the distress definition of measurement and the jointed plane concrete pavements module first. The first one we'll start with will be mid-slab fatigue cracking of jointed plane concrete pavements. Now, there are 5 learning objectives or outcomes of Module 5.1.1 on mid-slab cracking. The first is to define the fatigue cracks predicted in the P-Mid software. The second is to describe the PCC fatigue cracking strength model. The third is to define the allowable number of load repetitions used in the damage computations. The fourth is to define the incremental damage concept used for fatigue cracking prediction of jointed plane concrete pavements. And the fifth is to describe the transfer function for predicting mid-slab fatigue cracking in jointed plane concrete pavements. Now remember the 3 topics listed on this introduction slide, and they're going to be used or included for mid-slab cracking. So the first, we will define mid-slab fatigue cracking and how it is measured relative to the mechanistic empirical pavement design guide. So we're going to start with the definition and measurement of mid-slab fatigue cracks. The definition of mid-slab fatigue cracks are transverse cracks that extend across the PCC slab. The measurement is simply the number or percentage of slabs with mid-slab cracks as predicted by the Pavement ME design software and which were used in calibration. The numbers in the slabs, or the number of cracks in the slab, do not matter or impact the percentage of cracked slab. So one transverse crack across the width of the slab means the slab is cracked. If there are 2 transverse cracks across the slab, that still implies 1 cracked slab. There's also other types of cracking within the Portland cement concrete slab of a jointed plane concrete pavement, which we'll now cover. Corner breaks can occur, which are also a fatigue-related crack in the slab. So a slab with a corner break and no other cracks is counted as a cracked slab. Longitudinal cracks can occur, which are also a fatigue-related crack in the slab. So a slab with a longitudinal crack and no other cracks is counted as a cracked slab. The core, shown on the right of the slide, was taken along a roadway segment which shows a top-down crack in the Portland cement concrete slab. Now that we have defined mid-slab fatigue cracking, let's now discuss the distress mechanism for predicting mid-slab fatigue cracks of jointed plain concrete pavements. Jpcp fatigue cracks are caused by the repeated application of traffic and climatic loadings as tensile stresses less than the ultimate strength of the Portland cement concrete slab mixture. The repeated tensile or bending stresses applied at a given point develops microcracks that eventually form into full fractures at critical points along the slab. Remember the paperclip experiment from Module 2, where we failed a paperclip with multiple bends of the paperclip. In concept, the fatigue or failure of a Portland cement concrete layer is no different than for the paperclip. The fatigue strength is based on or dependent on a critical response and the strength of the material. The fatigue strength of the material is simply the allowable number of load applications or critical response applications. The fatigue cracking mechanism is defined by 3 parameters or variables, similar to the paperclip experiment that was demonstrated in Module 2. The critical response calculation is the first. The second is the material strength of the Portland cement concrete. And the third is the allowable number of load repetitions or applications. Sections of this module that follow will define and explain the critical response calculation for jointed plain concrete pavements, the PCC material strength, and the allowable number of load repetitions in predicting the fatigue cracking or percent cracked slabs of jointed plain concrete pavements. First, let's discuss and explain the critical response calculation of the distress mechanism for predicting fatigue cracks in jointed plain concrete pavements. Remember from Module 2, iSlab 2000 is used to calculate the responses of the Portland cement concrete slabs for designing jointed plain concrete pavements. iSlab 2000 is a finite element program. Millions of runs were made with iSlab 2000 to calculate the critical rigid pavement responses, which were used to create the artificial neural networks that were explained or noted in Module 2. The artificial neural networks in the P-Mid or Pavement ME design software are used to calculate the critical responses for predicting the fatigue cracking of the jointed plain concrete pavement. So, the jointed plain concrete pavement responses are calculated with the artificial neural networks and not iSlab 2000 itself. The rigid pavement responses of distresses and slab deflections are dependent on the wheel loads and their locations, the temperature gradients, through the PCC slab and the properties of the pavement layers and subgrades supporting the PCC slab. However, if you remember from Module 4, the inputs to the rigid pavement design procedure is resilient modulus of the underlying pavement layers. But the finite element response program of IceLab 2000 requires an effective K-value for the supporting layers. Thus, a conversion procedure is used in the PMed software to convert the resilient modulus of the supporting layers to an effective K-value, which is the input to IceLab 2000. So the layer inputs to the rigid pavement design procedure are the resilient modulus of the underlying pavement layers, but the finite element response program of IceLab 2000 requires an effective K-value for the supporting layers. A conversion procedure is included in the software to convert the resilient modulus of the individual supporting layers to an effective K-value. The elastic to K-value conversion procedure is based on the deflection basin, basically the calculated deflection basin. In summary, the elastic layer program is used to calculate a deflection basin for the rigid pavement using the elastic or resilient modulus of all layers. The software then uses the elastic, the mid-slab deflection basin to back calculate an effective K-value or composite K-value for the supporting layers below the base layer. Remember, the base layer can consist of a cement stabilized asphalt or asphalt mixture or granular aggregate material. Or even the PCC slab can rest directly on the subgrade itself. Now, for bottom-up transverse fatigue cracks, the critical response is the tensile stress at the bottom of the PCC slab. The location of the critical tensile stress is typically at the mid-slab location at the bottom of the slab and near the edge of the slab. Both traffic and climate forces or loads contribute to the magnitude of the tensile stress used to predict fatigue cracking. For top-down transverse cracks, the critical response is the tensile stress, but at the top of the PCC slab. The location of the critical tensile stress is dependent on the location of the axle and wheel loads, but is typically along the edge of the tires. Both traffic and climate forces or loads contribute to the magnitude of the tensile stresses. For top-down longitudinal fatigue cracks, the critical response is tensile stress at the top of the PCC slab. The location of the critical tensile stress is dependent on the location of the axle and wheel loads, but is typically between the wheel or tires on different sides of the axles. Both traffic and climate forces or loads contribute to the magnitude of the tensile stress for predicting top-down longitudinal fatigue cracks. For top-down corner fatigue cracks, the critical response is a tensile stress at the top of the slab. The location of the critical tensile stress is dependent on the location of the axle and wheel loads, but is typically along the edge of the tires or in front of the tires or axles. And both traffic and climate forces or loads contribute to the magnitude of the tensile stresses for calculating top-down corner fatigue cracks. Now let's identify the material strength of the PCC layer used in the stress mechanism for predicting fatigue cracking of jointed plane concrete pavements. Very simply, AASHTO T97 is used to measure the flexural strength or modulus of rupture of the Portland cement concrete mixture and layer. Remember the different input levels for the PCC strength as a review from Module 4.4.4. The first is the flexural strength or modulus of rupture at different ages. The input level 2 is the compressive strength at different ages, and input level 3 is the flexural strength or compressive strength measured at 28 days or calculated from the regression equations embedded in the Pavement ME software. This was all discussed in Module 4 on inputs, specifically for Portland cement concrete mixes. Next up is a discussion on the allowable number of load applications to induce fracture for the distress mechanism in predicting fatigue cracks of jointed plane concrete pavements, just like the paperclip experiment demonstrated in Module 2. The number of load applications or repetitions was measured in the laboratory using repeated load bending beam specimens. The applied tensile stress determines the number of load repetitions for that specific tensile stress. However, most of the PCC fatigue models are now based on the stress to strength ratio, as shown in the graph displayed in the slide. The stress to strength ratio was found to normalize the difference between different PCC mixtures with different flexural strength or modulus of rupture values. In summary, the number of load repetitions is defined by the ratio of stress to strength used to determine or measure the number of stress repetitions or allowable number of load applications. The strength is defined as from the beam flexural strength, or AASHTO T97. The stress is defined as bending or tensile stress that is calculated at the bottom and or top of the beam. In summary, the MEPDG PCC fatigue model to determine the allowable number of load repetitions was defined from field testing or field loading and full-scale testing of Portland cement concrete slabs, which is shown on this slide and is defined by the strength or modulus of rupture measured in accordance with AASHTO T97 and the maximum tensile stress calculated at the bottom or top of the slab relative to the wheel loads and slab geometry. As such, the allowable number of load repetitions or applications vary with time. Top and bottom of the PCC slab, and location along the slab relative to the axle load geometry. The fatigue cracking mechanism includes calculating the Portland cement concrete incremental fatigue damage and summing it to demonstrate the total fatigue damage over time and within the PCC slab. This section or session of the module will explain and discuss the accumulation of the incremental fatigue damage in the Portland cement concrete slab. First, what does the incremental fatigue damage accumulation mean? And or how is it determined? Remember from Module 2, the fatigue damage is the result of the actual number of load applications divided by the allowable number of load applications, just like what was demonstrated from the paper clip experiment in Module 2. The incremental fatigue damage is summed using Miner's hypothesis or damage equation, which is displayed on the slide. The damage is calculated based on the critical responses, tensile stress, computed by the artificial neural networks developed from the IceLab 2000 finite element program. Tensile stress is calculated at the top and bottom of the PCC slab at different critical locations based on the axle load geometry within the time increment of the time of day. However, many of the pavement inputs do vary throughout the year, throughout the season, and throughout the day, as well as with wheel loads. So this is the fatigue damage accumulation is simple in concept, but there are many calculations of the actual number of load applications within a specific axle load, specific time period or climate, and location of the slab divided by the allowable number of load applications for that same specific condition. In summary, the design life is divided into time and load increments. Some of the pavement and traffic variables that change over time for which the Pavement ME design software considers are the PCC strength and elastic modulus of the material, the moisture gradients and shrinkage of the PCC slab change throughout the design life, temperature gradients change throughout the day, nighttime and daytime, as well as curling and warping of the slab itself. The number of axle load applications also increase over time, and the different types of trucks may have different or do have different axle and tire geometries. The base layer can erode at different points of time, and the base PCC slab interface can degrade over time, which has an impact on the tensile stress at the top and bottom of the PCC slab. The saturation elastic modulus or the subgrade elastic modulus varies over time depending on the degree of saturation. As such, the Pavement ME software is an extensive bookkeeping process to calculate and accumulate the fatigue damage throughout the PCC slab and throughout the design period or design pavement life for a specific design strategy. In summary, the fatigue damage is accumulated through the design period, considering all of the variables listed and noted on the previous slide. The fatigue damage for top and bottom up fatigue cracks are listed in the output report, which is graphically illustrated in the figure or graph displayed on this slide. So this damage is accumulated throughout the design life of the pavement. And those time-dependent variables or time-dependent fatigue damage of mid-slab cracking are accumulated over time throughout the design period. The P-Mid software calculates the maximum accumulated fatigue damage over time using Miner's hypothesis or fatigue damage concept as previously discussed. But how does the fatigue damage get used to design jointed plain concrete pavements to limit the percent cracked slab to a specific value? The answer is through the transfer function as defined in Module 2. So moving on to explaining the transfer function for mid-slab fatigue cracks of jointed plain concrete pavements. Remember from Module 2, the critical pavement responses are used to determine or calculate fatigue damage from all of the inputs, the climate, traffic, the layer inputs, the response variables. For mid-slab cracking, it's basically tensile stress at the top and or bottom of the slab. And the transfer function converts that fatigue damage to what we can see and measure on the pavement surface, which in this case is the percent cracked slab of a jointed plain concrete pavement. The graph displayed in this slide is an illustration of the transfer function for jointed plain concrete pavement fatigue cracks or percent cracked slabs. The transfer function is defined through the calibration process by relating the accumulated fatigue damage to the amount of fatigue cracks at specific times for many different jointed plain concrete pavement sections. So for each measurement of percent cracked slabs, the calculated mid-slab cracking fatigue damage is related to the percent slabs cracked observed for a specific test section and specific point in time. This slide is a graphical representation or process of the procedure used to calculate the amount of Jpcp fatigue cracks. In summary, the fatigue damage is calculated over the design life for a specific Jpcp cross-section input variables and site factors, kind of as shown in this slide at a specific age or time. The transfer function is used to convert the fatigue cracking to a measured cracking value from the calibration process. The amount of fatigue cracking is displayed by fatigue cracking predicted over the design life. So basically the transfer function simply transfers the fatigue damage to a percent cracking value over the age or design life of the project or design strategy. And so we see that we have so many percent cracked slabs as a function of age. And this is used to then determine the reliability of our design strategy to ensure that the allowable number of fatigue cracks is less than our predicted number of fatigue cracks at the end of the design period. The regression equation displayed in this slide is the Jpcp fatigue cracking transfer function defined through calibration. In other words, converting the fatigue damage to a measured cracking value or percent cracked slabs. The C4 coefficient has a value of 0.431, and the C5 calibration exponent has a value of negative 2.303. The values for C4 and C5 may vary between different publications of the MEPDG Manual of Practice depending on the results of any calibration that has been completed more recently. The coefficients and exponents of the transfer function are also included in the output report for the PMID software. The graph displayed in this slide shows the predicted amount of percent slabs cracked over time in comparison to the measured values for a specific roadway segment that was included in the global calibration process. The percent cracked slabs begin very slowly, but then start to accelerate over time with higher amounts of truck traffic and higher amounts of damage. This slide summarizes the coefficients that were used to calibrate the transfer function or model in predicting the total percent cracked slabs throughout the design period. These calibration coefficients include C1, C2, C3, and C4, as defined on the slide. As noted previously, however, the values for the calibration coefficients may vary between different publications of the MEPDG Manual of Practice, depending on the results of any updated global calibration process of the rigid pavements. The coefficients and exponents of the transfer function are also included in the output report for the Pavement ME design software. Reliability was discussed in detail in Module 3, and how reliability is applied in the Pavement ME design software. The standard deviation of the residuals for the jointed plain concrete pavement percent slabs cracked is displayed on this slide. The standard deviation of the residuals is used to determine the reliability as related to the Jpcp percent cracked slabs. Again, reliability and how it is used was discussed in detail in Module 3. This section is a summary or wrap-up of the materials presented under Module 5.1.1 for jointed plain concrete pavement fatigue cracking or mid-slab cracking in terms of percent cracked slabs. In summary, we defined and explained the PCC fatigue cracks of jointed plain concrete pavements. We described the PCC fatigue strength relationship included in the PMID software. We define the number of allowable load applications that are used to compute the fatigue damage for a specific condition. We define the incremental damage concept used to predict percent cracked slabs of jointed plane concrete pavements relative to Miner's hypothesis. And we describe the transfer function for mid-slab fatigue cracks. In other words, describing the transfer function relating fatigue damage, total fatigue damage, to percent cracked slabs. This ends Module 5.1.1 on Jpcp-Mid slab cracking. The next submodule of the training course sequencing is Module 5.1.2 on Jpcp faulting for rigid pavement design.